When you let water down your toilet, down your sink, down the drain, it all goes into the sewer. And a lot of us don't know this part, but a lot of the water gets treated for reuse. I was talking about this with today's guest. I actually studied that in school, like 12, 13 years ago. So I might have a little. So we're just talking if it's about the technical part about it. But the thing is that when this water is treated, the solid parts of the water, you have the water and you have the solids in the water. The solid part, most of the time, has been a challenge to deal with generally. And today's guest on Greentech Pulse has a solution for that. Today's guest is Garrett. Garrett is from Bioforce and Bioforcetech, and he will be talking about biosolids, treatment of wastewater, and everything around that. So, welcome to the Greentech Pulse, Garrett.
Thanks for having me, Peter. It's great to be here.
Thank you so much. So, what led you to doing this?
Yeah, so I joined Bioforcetech about 8 years into their development when they were installing full scale and had a material coming out of their machines. So they're taking biosolids or the output sewage sludge from wastewater treatment, and they're turning it into this carbon negative material. And I happen to actually be studying my master's in industrial design at Pratt Institute in Brooklyn. And I was looking around doing research on sort of society's interface with waste and disgust. So, why do we think things are dirty? Why do we think things are disgusting? And I learned about this biosolids problem and thought that this was a perfect way to use a material for better use that people think is disgusting. And so, working with the New York City government, working with bioplastic startups, and looking in scientific literature, I designed a pen and ink that could be made from sewage. And so it was viable, had research and economics behind it, but was obviously meant to be conceptual, so you would be chewing on your pen or writing a note on your hand. It would change that line of what's acceptable, what's useful, what's valuable, what's a waste. And I went with the New York government representative that I had gotten to know to a biosolids conference after I graduated to see what that world is like at a professional level and see if there's opportunities to sort of scale this research or have new ideas. And Bioforce Tech presented their technology that's giving a service to municipalities of volume reduction and contaminants destruction that is resulting in this same carbon material as the pigment that I conceptualized in my pen. So it was a match made in heaven. So I immediately, gave a copy of my thesis to one of the founders and kept in touch. And a year later, when they received investment to develop the material output from their systems, they offered me a job. So that was 2020. That was just about 5 years ago, this August. And that's how the material Our Carbon, which is the name of the material coming out of their systems, was born.
Okay, so you're creating our carbon out of the biosolids from wastewater.
Exactly, through the Bioforce Tech system. So it's the name of the product through Bioforce Tech. It's all under the same umbrella. It's Bioforce Tech's product, but we give it a different name, different attitude because we're working with so many different audiences, from automotive and fashion to built environment and concrete.
Okay, so I think before we go into our carbon, let's talk
Yeah.
about biosolids. I know we are being fancy with it. So, so when we talk about biosolids, what exactly are we talking about? Then from there, why are they a challenge when processing or taking care of wastewater?
Yeah. So, it's not a big cover up. The reason that biosolids have a different name than sewage is that there's such a massive amount of treatment that occurs in the wastewater system that at the end it is, a bit of a different material. So it does deserve its own name. I promise I'm not covering anything up. But so yeah, so wastewater treatment is a pretty complex process, and depending on how old the city is, how big the tax base is, how much investment they've had in their treatment, there can be different levels. So if you have a centralized sewer system, so if you flush a toilet and it goes into a massive, a centralized sewer, you're going to have some amount of treatment, whether it's settling, lagoons, et cetera. At the base level, sometimes it's very little and it just goes out into a waterway. And that's that was a problem. That's what was happening even in the US until the 70s, until the Clean Water Act in 1973. Nowadays, there's a lot of different sets of systems that can both clean the material and pull nutrients. So people pull phosphorus, they settle out different minerals, they sort of clean and screen, and it's a whole chain of events. But at the very end, no matter what you're doing across the way, you have to separate the solid material from the water and try and use both of those beneficially. The water is something that you hear about a lot. Gates Foundation has processes making drinkable water. There's water reuse in Singapore, et cetera, where they're able to even make beer out of that water. But the solid material is very concentrated with contaminants, and it's harder to make a beneficial use of, right? So if you imagine basically a centrifuge or some kind of a juice press, right? That's the last stage, is trying to just press out that solid material. But even then, you only get it to about 20% solids on average if you have what's called dewatering. So you're left with this sort of sludge. And that's biosolids. And today, the vast majority of biosolids are either spread on land as like a small grade fertilizer, or it goes to landfill. And both of them have reasoning, but they both have issues. So if you spread the material on land, it's basically a manure, just like a cow manure, things like that. So there is a biological carbon, there's some nitrogen and phosphorus that would be beneficial for crops, but there's also everything that went down the drain and concentrated in it. So pharmaceuticals, microplastics, microfibers, heavy metals, forever chemicals like PFAS and PFOA, it's all concentrated in the biosolids, and it goes into our soil environment, our crops, our water. So that's in the US and in a lot of parts of Europe is being outlawed, and that's causing the fee per ton to go up for the municipality to manage. And the other side is landfilling. So if you landfill, yes, you control those contaminants to an extent, right? You're going to contain it in the landfill. But when you cover up such a active and organic material with other garbage and you cut off oxygen to it, you create methane instead of CO2. And so methane is 84 times as potent as CO2 in the greenhouse gas potential. And so you're, multiplying out the global warming effect of the material, and you're not using the material for any benefit. So that's what's happening today. And from a taxpayer perspective, every truck that leaves the plant, the wastewater treatment plant, has to be paid to get rid of it because it's a waste. So your taxpayer dollars, if you're paying taxes in your city, that goes into the infrastructure for the sewage treatment, and it goes month over month, ton over ton, to the haulers in the middle that are paying to haul away the material. So as regulation against greenhouse gases and against land application, as landfill space dries up, as population increases, and so there's less places to put the material, that fee is rising and rising every year. So that's sort of the biosolids burden, as we put it, and that's what we have a solution for.
Interesting. So, I know I was a bit caught up when we were explaining it. So, it's like choosing between two evils. You can use it as a manure on the soil, but you end up with all the contaminants, pharmaceuticals, and whatever that were in the original sludge. Or you can use it in landfill, which make putting it in an airless environment creates methane, which is another problem. So I think that makes the need for Bioforcetech technology glaring. So now, can you explain how the technology works? How do you turn this thing that either ways manure or landfill is a problem into something as useful as pen and ink?
Yeah, totally. So what we provide to the treatment plant, if you're looking at it as, let's say you operate a wastewater plant and you're sick of paying this cost to get rid of your sludge, is that we take 10 tons of sludge of biosolids at that 20% solids, and we can turn it into 1 ton of our material we call our carbon. And we destroy contaminants along the way, and it doesn't require a very large energy load at all. It's actually net zero from a thermal energy perspective. So it sounds like perpetual motion. Let me explain it. But that's what we provide to the treatment plant. So they buy the system, and now they're going to spend only 1/10 of the money on the trucks leaving the station, right? And they're going to meet those regulations. So the way it works is with two different machines. So the first one is a drying machine, which is simple in theory, but it actually takes a lot of energy if you do it the normal way. So, like I said, biosolids is 20% uh, solids when we receive it, right? So it's 80% water. And it takes a lot of energy to evaporate all that water. Fun fact, it takes actually 10 times the energy to evaporate 1 kilogram of water as it does to melt 1 kilogram of aluminum. So it's very, very energy intensive. If you think about how long it takes to boil water versus to heat up the pan, water is a big factor. So if you were to dry biosolids normally, it would cost a lot of energy. So a lot of natural gas, a lot of propane or electricity, whatever you're using, which translates to dollars. So it costs a lot of money. And the carbon balance doesn't work where if you then make the material into our carbon, you're actually spending more CO2 to make the material than you are fixing inside of it, right? So you're not providing a benefit. So Bioforcetech looked at some way to try and dry biosolids that doesn't use all of this external fuel. And they decided to actually take a biologist approach. So if you have a compost pile in your backyard, or if you've made sourdough bread or kimchi or fermented yogurt, you know that biology is present in lots of materials, and as it becomes active, it makes heat, right? It warms things up. So that's what we do. The machine is called a biodryer, and it's basically a container that can roll like a cylinder that we fill with 8 tons of biosolids at 20% solids at a time. And we pass air through the material from the bottom up in that container to give air and oxygen to the material and the bacteria that's living in it. It's naturally present bacteria. As that bacteria gets oxygenated, it gets happy and flourishes and starts multiplying and doing its bacterial thing, and it creates heat. So I like to think of it as a nightclub, right? You just supply the booze and make the music right, and the dancing is what makes everything hot, right? So it's very similar. Okay, so we're passing air through this material, we're managing the situation, making sure that the levels are correct, and the bacteria are having a good time and making a lot of energy and bringing the temperature up. So that allows us to dry the material out almost completely, managing just that bacterial heat. It's very low temperature. It's about 150 Fahrenheit. So that's the same temperature as like high-end saunas. So it's really not super, super high temperature, not a very dangerous process at all. And if you just have dryers installed, it runs at the same time competition as other dryers, but at 30% of the energy load. So it's a 70% reduction in the energy required. At the very end of the process, the material does get a bit too dry for the bacteria, so the bacteria go dormant. We still need to remove a little water, so we use a little bit of external heat. If you just have dryers, that does require natural gas, and that's why we have 30% of the energy load. But if you have our second step, we actually create heat at a very high temperature from the material again, a different way. And that provides that final bit of heat instead of natural gas. So if you have the full Bioforcetech system and you're making the carbon material, you don't actually need any external energy once it's running. So that's the drying step. It's honestly, it's pretty great in and of itself. We have 34 dryers operating in Italy and USA, and we have another 16 being built already. So we just passed our 50 biodryer milestone, and the factory is absolutely full of biodryers being built. So it's a really great machine that can already help the quality of the biosolids by drying it out and helping destroy certain viruses, bacteria, things like that. So
Okay,
that's
so
step
that
one.
yeah. Okay, so I think when you mentioned the part about the heat coming out from bacteria, I actually started compost. You talked about compost. I actually started composting, I think a year or two ago. So the first I got horse manure um, towards the end of last year. I got the bag. I kept it in my garden. Came back 2 days later, opened it, and there was actual smoke coming out of it. So I think that's what you described reminded me of actually.
Yes, exactly. So it's like a controlled steaming compost process, right? It's like a speed compost. So if you were to contain that heat, you could keep circulating it and make the temperature go up and up and up and dry out your compost. So that's what we're doing with biosolids. So yeah, so that's the drying step, and we can turn 20% solids into 95% solids, even so, almost completely bone dry if we want to, just with the biodryer alone. But that's very, very, very important, not the transformative step. Okay, so the next step is what actually turns the material into our carbon, as we call it, that carbon negative output, and what destroys the contaminants. And that's called pyrolysis. Have you heard of pyrolysis? Yeah, something like that. So yeah, let me explain, because that's really the key part, is what makes it different than burning. So pyrolysis is basically the process of heating material in a controlled way without oxygen present. So if I take a piece of paper, or a banana peel, or a shirt, anything with carbon in it, and I light it on fire, the carbon in that material is going to bond off to the oxygen and everything in the air, and that's why you get CO2 and a flame. And what's left is the ash, which is just the mineral parts that can't burn. Okay, if you do that same process where you're taking something carbon based and heating it very high, but you cut off any oxygen to it, so it's in a controlled, contained environment, uh, some of the carbon will make a burnable gas. We call it syngas, and that's how we create heat. But the bulk of the carbon, once there's nothing left for it to attach to, um, it wants to trade off molecules and change phase, but it can't. So instead, it bonds to itself and forms these really tight chains of carbon. Okay. So the bulk of the carbon is stuck and fixed in place with these tight bonds. And of course, the ash is still there, that mineral fraction that could never burn. So that's what the material is that we produce. So the way it works is we use natural gas only for a couple of hours to heat up the outside of a chamber to over 650 Celsius. Okay, so very hot now. Um, we put biosolids through that chamber, and it's, picture a long tube with a screw conveyor in it, right? An auger. So we're pushing material through this reactor. And as it gets hot enough, the biosolids, it splits into that gas and the carbon. The gas gets brought into a chamber where we use it right away for heat, and we pass that heat back around to take the place of the natural gas. So you're putting in material, you're forming a gas, you're using that for heat, and now that is the fuel for the next bit of material. And what's left, what comes out, is that our carbon material that's got fixed carbon and has all those contaminants destroyed. So now you're making enough heat to keep the process going. You're making a material that has no pharmaceuticals, no PFAS, no microplastics. So we've been proven even by the US EPA to destroy PFAS. And you have so much heat left over to share that we can push heat back to the dryers to take the place of any of that natural gas that would be needed. So once it's all together, you have enough heat provided by the bacteria and then by the syngas in the second step to make the whole thing energy neutral from the thermal heat perspective. So it runs on itself.
It's actually a very interesting process, and it actually reminds me a lot about chemistry from long, long, long ago.
Yeah, yeah, it's a thermochemical process. It's really interesting, and it's nice to be using the material itself at each step, biologically and then chemically.
Exactly, exactly. So that means from your description, our carbon is from everything that's created. You now have solid carbon created from the biosolids, solid carbon and ash.
Yes, so and it's together in a sort of grain. So you can think of it as like a black sand. That's what it looks like and feels like. It's this durable carbon-like material. Yeah, which is very unique. So if you're listening and you've heard of the term biochar, that's similar to what we're making, but many people, no, very few people are making biochar from biosolids. And making it out of this material makes it very different than making it out of, let's say, wood chips or nutshells or things like that. So it's sort of like a charcoal, but because of this ash material and the sort of granular shape of it, it has these really unique characteristics that we can use in industry.
All right. So I think earlier you said that you mentioned the pen and ink example. Then you also mentioned that our carbon can be used in different industries, construction, and for other things. So can you share some examples of where it has been used?
Yes. So there's two major ways that we use our carbon. So the first is for its ash fraction, let's say. It makes it very durable and has these different minerals in it. And so we can use it in the built environment to store carbon. And that's a very high volume use. So we can use it in structural grade concrete as a partial replacement for sand. And what that allows us to do is to put many, many pounds per cubic yard of the material into structural grade concrete without hurting the structural performance. And so we can store that carbon in the built environment long term and turn down the carbon footprint of concrete. If you don't know this, there's a really nice fact to walk away from here. So cement is the second most used material by man, second only to water. So it's the most used man-made material, and it's 8% of global emissions. And cement is the main component in concrete. Concrete is basically cement and aggregates of different size, right? So by taking this very, very high carbon footprint material and adding our carbon into the concrete mix, we're able to store that carbon against the carbon footprint of the cement and equal out a much lower carbon footprint. So we call it insetting. So instead of offsetting something somewhere else, you're insetting the carbon into the material itself. So that's a really strong long-term storage where you can really trace and track the carbon. You can say the carbon is right here in this building and the carbon benefit is tied to that building too. So that's a really, really nice way to make the whole city circular. You can take the city's waste, turn it into this carbon and put it back into the city as you build it. So it's a really nice, local, easy to use and understand story. So that's the first way we're using it. The second way is as a black pigment. So if you are wearing mascara right now, if you drove in a car with black tires, if you're typing on a black keyboard, the material that makes all of that black is called carbon black. And it's almost everywhere. Once you know this, I promise you, you're going to see it everywhere. So carbon black is made by basically burning fossil fuel byproduct and collecting the soot. And so it's a class 2B carcinogen. It's very emissive. It takes, on average between 3 and 5 tons of CO2 to produce it. And it's everywhere. So we can replace carbon black in a lot of different applications, from furniture and furnishings as a polymer additive and pigment, to fashion in screen printing inks and footwear components, even to automotive like dashboards and things like that. So that's scaling in all different ways for use as a replacement for carbon black. So we say that we divert by stopping biosolids management practices, then we transform with our technology, and then we apply. And each one of those steps has an impact. So all of that is in the application stage of concrete and pigment.
Okay, so this is actually really, really interesting to me. So
Yeah.
okay, so you build your plants in different waste treatment plants. I know you mentioned you have some in Italy, in the US, and co. And then you do they pay for you to treat this? Because I know you mentioned earlier that otherwise they would have paid people to take this from them, but you're converting like 10 tons of whatever they make into 1 ton of um, biosolids. So how does it work with these waste treatment plants? Then apart from that too, what sort of organizations do you work with? Is it just the waste treatment plants or maybe the manufacturers for that use the carbon black that would have used the carbon black and all these other things?
Yeah. So for me on the output side, on the R carbon side, it's really fun because I'm involved with all different industries. So I'm involved with wastewater treatment operators, talking about the machinery. And then I'm also meeting with government people about their landfill goals, their landfill avoidance goals. And then I'm also with, automotive companies and fashion groups and screen printing manufacturers and polymer compounders and all these different industries, architects and engineers. So it's very interesting to hear the sort of global conversation around achieving carbon goals from all these different groups, because everyone talks about it differently, understands it at different levels, and has different needs on their side. So that's been really fascinating for me. On the equipment side and the wastewater side, um, the municipalities actually purchase our machinery and they own and operate it, right? So they have a need to reduce those fees to destroy those contaminants. So they buy the system and they install it, but we guarantee an offtake of the material. So we're working together with the municipality to make that happen. So they don't pay a tipping fee anymore. So they've reduced it to 10% of the original mass. They don't pay a tipping fee. We take the material with no questions to them. And then we actually share a small profit back, a percentage of what we can make back to the municipality. So you're taking, let's say, just for the sake of it, it costs $100 a ton to get rid of the material, right? So every 10 tons is $1,000. So now, no matter what, you're turning that into only $100 because you're taking 10 tons and making it 1 ton. And then instead of $100, we're actually going to take it for free. So you don't have to worry about managing it. And you're going to get, let's say, $30 back. Okay. So altogether, you $1,000 of loss into $30 of profit for installing this system. So that's what pays off the system for a municipality over time, because of course you have to pay for the system to install it.
Oh, so this is like a win-win situation for municipalities who install it. But what are the challenges? Is it like is there a minimum size of waste treatment plant it works with, or does can it work with all sizes of communities?
Yeah, so for both units, so the biodryers and the pyrolysis, the Sigma pyrolysis unit, as we call it, um, there is a minimum size and a maximum size because of the footprint. So wastewater treatment plants think about their scale on the scale of MGD, which is millions of gallons a day, which is also just a crazy thing. Imagine millions of gallons a day of sewage coming into a building. That's what they're thinking about every day. So our in the U.S., about 80 or 90% of the wastewater market is 1 to 12 or 1 to 15 MGD. Okay, and our system is sized for that scale. So our sweet spot is between 1 and 12, maybe 1 and 14 MGD. But you need around 3 MGD before you can have a pyrolysis unit. So each million gallons per day is enough roughly for one biodryer. And once you have 3 biodryers, you can install a pyrolysis unit. So they're all prefabricated. They're the size of a shipping container. They're about 40-foot containers as far as what they fit inside of. And so we just put them down as units depending on how big the plant is, or if they're going to grow, because a lot of places are gaining more population. You know, the population is going up. So we have 3 in 1 is our base system, right? 3 dryers, 1 pyrolysis. We have a system going in that's 8 and 2. We have some systems that are just 1 biodryer, so that a small municipality can just reduce their volumes by drying, but they don't have enough room for pyrolysis. So that's how it varies. Once you get to that 15, 20, 30 MGD, like a big city like San Francisco, um, then you have some trouble because you have all of these containers, right? So it starts to look like a trailer park of Bioforcetech units of this huge city. So that's where it starts to be more difficult for our system to make sense in the immediate, where maybe you look at conventional drying and just pyrolysis or something like that. So it's a great question. Yes, around 1 to 12 MGD is our sweet spot, and we're installing right now in the 10 MGD or so and lower.
Okay, so I think, and like you said, you need at least 3 MGD to have a pyrolysis unit.
Yes, yes, to have enough flow. Yep, that's right. Well, just the way that that translates as well. So this is usually, the next equation. Okay, so if you have 3 MGD, how much wet biosolids do you make on the end? You make about 3,000 tons. So it's likely roughly in powers of 10. So 3 MGD makes 3,000 tons. Each biodryer processes 1,000. So that's how you have 3 biodryers. And then we turn that 3,000 tons into 300 tons of our carbon. So that's sort of the rule of thumb. Each MGD is 1,000 tons wet, and then it's 100 tons of our carbon in the end.
Wow. Oh, wow. So I think from your description, from the benefits going from, I know you mentioned like $1,000 of cost going into $30 of profit. It's something that almost every large or medium scale municipality should have. So what challenges has Bioforce Tech faced scaling this, getting this everywhere?
Yeah, so I think for better or worse, Bioforcetech took on the most challenging way to do this and material. I think they could, and it's allowed us to get to a really really advanced system with really strong permitting and things behind it. But they really took on a unique challenge. So um, the first one that is always a question is permitting. Okay, so making sure that you're not releasing chemicals or emissions into the air that we don't want. The Bay Area Air Quality Management District is a very, very strict air permitting group, which is great. We need that. But it means that it takes a very long time to get permitted. And with a new process that's different than other processes, you need to prove from scratch that you're not causing any harm. So one of the biggest milestones for Bioforcetech was getting that permit in the Bay Area of Silicon Valley, which took 4 years. But it's because it's so rigorous, it shows how strong our emissions controls are. So that can slow things down. And now that we have had the Bay Area permit and we've been running full scale operational in the Bay Area, that's been really strong. The other side is just a new technology, right? So um, there's a fear from the municipal side that if something is too complicated to manage yourself, or if it could break down easily, you're going to install something with your family's money, right? Your taxpayers' dollars, your friends, your family in the town, and it won't work. So it's an industry that is very much about the proof in the pudding. They're like, I want to see these things running long term. I want to visit. I want you to make samples from my material, et cetera. So that makes the adoption rate for new technologies in wastewater and infrastructure slow in general. We're the first ones doing this in North America, first and only full scale operational biosolids pyrolysis. So we've led the way in showing people that this is possible. And now we're at this great scale up moment. So we have 3 systems that have pyrolysis attached to them in the US right now. And we have 2 more units already being built to join those systems. And we're scaling from there. And the biodryer was developed a bit earlier, so it's ahead of the pyrolysis unit. So we already have, like I said, those 34 or so operational units of biodryers. So we're getting there. But yes, it was definitely a long road, let alone getting the bacterial process to work and things like that. But it's allowed us to come out with a very, very well engineered machine that takes a material that's very hard to process and can successfully do that. And that's what excites me. So I'm also looking at what this technology can do for other biomass, for other inputs, because it's so advanced and so well engineered. So that's also a really great opportunity to say, okay, biosolids is very hard to process. It's very highly regulated as a waste. And we have successfully permitted in a very difficult to permit place and are now running. What would happen if we process nutshells? How can we process wood chips? Can we process other sludges, pharmaceutical or food and beverage or paper mills, to make new forms of our carbon that are very highly engineered? So that's really exciting too, and opens up the door to an expanded future.
So now, in your opinion, when this sort of technology is widely accepted, this way of processing biosolids is widely accepted, what kind of environmental impacts would you think it's going to have globally?
Yeah, that's a great question, Peter. So the impacts are really huge, and I want to take it from each of those 3 stages. So divert, transform, and apply. So we've talked about landfill and contamination, et cetera, but I want to put some numbers to it. So in the US, we have developed a life cycle assessment using the standard models, and with a third party verification that looks at the impact of avoiding landfill by stopping these biosolids from going there. Okay. So we split it up into 4 different regions of the country based on their climate. So the more humid and hot an area is, the more methane you produce in a landfill. Similarly, the less processed the biosolids are in the treatment plant, the more carbon is available to become methane. Okay. And then finally, the less regulated the space is, the more open and less controlled the landfill is. And so the more methane will go into the atmosphere. So those are three dials that we created for this LCA, this life cycle assessment, to see what would happen. So in the most emissive area of the country, which in the US would be Florida, New Orleans, the Southeast, where it's very hot and humid, and with the least processed biosolids and in the least regulated landfill, so the most methane being made, every ton of our carbon that we would produce from those diverted biosolids would avoid 24 tons of CO2 on a 20-year methane basis. And that's huge. So if you drive a car, an average gas car emits around 4 or 5 tons a year of CO2. And we make 300 tons a year, sorry, from our process. So it's almost a ton a day, which means you're taking a car off the road for 5 years every ton that you make uh, from this system if we were to install in these highly emissive areas. The areas that we're installed in right now are still quite high. They're on that 1 to 10, 1 to 14 level of avoidance, but that's the maximum that we could hit in America, which I really want to make happen. So that's really strong, and that's just from diverting the biosolids. Then you have the transformation step. Okay, so when you transform a material, it always takes energy. But as you know, we're using bacteria, then we're using the material itself. So it's all extremely low inputs. So our entire process only takes zero point zero 0.08 tons of CO2 to complete. Remember when I told you about making carbon black, that emits around 3 to 5 tons. We're talking about 8 hundredths of a ton to make this process happen. Okay. So very, very low energy in the transformation. And then you're fixing the carbon. So that fixed carbon by weight equals just over 1 ton of CO2 removed from the atmosphere. Okay. So now you have negative 1 ton total in the material itself. Then you go and store it in concrete long term, or you replace carbon black, which emits around 5 tons. So that's on the apply side. So let's do the math. In a best case scenario, we've avoided 24 tons, then we've fixed over 1 ton, and then we've avoided another 5 tons by replacing that carbon black pigment, for example. And you have a total impact of 30 tons of CO2 per ton of production, with a mix of both avoiding and removing. And you're sort of rewiring, landfills, waste treatment, fashion and automotive all in one process. So that's really exciting. And of course, the human health impacts of removing the contaminants and all of that from agriculture is also quite impactful. So that's just the carbon impact, but it's very, very strong. And there's millions of tons of biosolids being produced in every country. So there's a very, very high impact potential. A lot of people are looking at biomass of all different kinds. And I love to do this pop quiz to ask people, imagine a biomass material, an organic material that is not bound by geography, that is not bound by seasons, that is regenerating everywhere, wherever people are, and that costs money to manage and is contaminated right now. It's it's actually a very unique biomass to have sewage sludge or biosolids because you're not bound by the seasons. It's not bound by the harvest. And the material itself really, really is causing harm today and needs to find a value. Whereas a nutshell or a wood chip, for example, has a lot of potential to be used a lot of ways. And so I'd rather see those things turn into other materials and other value added products before we go and transform it into our carbon. But biosolids is a really unique opportunity for something that's always going to be here and is always made.
This, and I think I would really love to see this everywhere. And really wish Bioforcetech a lot of luck and a lot of a lot of this thing spreading this technology everywhere, because like you said, biosolids are everywhere, sewage is everywhere, and it's produced every day, and it's probably not going to stop as long as we are on this earth.
Yeah, I don't think so. Even if we leave this earth, we're still going to be doing it. So yeah, I'm really proud to be a part of it. And the two websites, if you want to learn more, is bioforcetech.com and then ourcarbon.co. are the two different websites. And there's great animations. The machines are complicated. It's a hard process to imagine by voice. So it's really great. Go look at the videos, look at the animations of how everything works. I think it'll make more sense for you if you're listening and are a little bit lost at this point.
All right, so bioforcetech.com and our carbon.co.
Yes, that's right.
Yes. All right. So both of them will be, for those watching on video, they'll be on the screen. For those audio, it will be in the show notes. So you can go see the diagrams. You might even get some of the diagrams to put on the screen for the episode to make it easier. Because I know I studied this in school. You work in it, so it might be easier for us to understand than anybody else. But it's a really, really interesting topic. I think starting this podcast, I didn't really know. I wasn't really sure what I was going to find out, because it's like this whole space is just like a passion to me, something I enjoy. It's not really my work, but I think I've learned so every episode I learned so much. I really enjoy the conversations, and it's great seeing all the things being done in the green space, doing done for sustainability and everything. So thank you so much for coming on. Thank you so much for sharing with us your technology, your insights, and everything today.
Yeah, thanks for having me. It's this is what's needed. I think a lot of technology is here and ready to go, but we need people to understand it and advocate for it and be excited about it, because it's really easy to be pessimistic these days. So we need to keep the optimism up and work together to make these things happen. So thank you for spreading the good word and for having us on the show.
Thank you so much. So, for the listeners, I hope you enjoyed this as much as I enjoyed this. I hope you advocate to have Bioforcetech technology in your city to take care of your biosolids. And if you found this episode interesting, useful, helpful, share it with someone else who you feel is going to help. And if you want to learn more about the Greentech space, we have a lot of other episodes on different things, attacking different aspects of sustainability and the green space. So go through the episodes, and until next week, we're back with a brand new episode. See you. Bye for now.